All right. So guys, I don't know if I shared with you this story when I taught this material to you last year, but if I didn't, it's worth repeating. So when I student taught, frighteningly 23 years ago, I had just finished up my degree in chemistry. My senior year, I took a class called Inorganic Chemistry, and all that we did for the entire year was talked about the structure of salts and the electron structures of atoms. I walked into my student teaching experience feeling like I knew how to teach SP, D, and F. I knew the stuff cold. I understood all the waveforms. I got up in front of a class and realized this was about this time during my student teaching experience. Classes of 20 kids, because I didn't student teach in Utah, really bright, motivated people. Every single one of my general chemistry classes was operating really at an AP level. If I showed you the work that I had my kids do when I was student teaching, a lot of you would accuse me of being abusive because we did a lot of really high-functioning, high-level work that if I did now, my phone would ring off the hook because your parents would be concerned that you'd never get into BYU. So all of that to say, we're working really hard. This is going great. It's sort of this dreamlike experience. I go to teach this stuff to my very first class, student teaching, and oh my gosh, I mean, I look like a deodorant commercial because I was 15 minutes into this. I'm dripping in sweat. Clearly, nobody has any idea what I'm talking about. And guys, finally, I just had to say, guys, time out. We're done. Clearly, this isn't working. I had to stop the day, not teach anything to the rest of my classes that day, and just come back and regroup and apologize to my kids and go, wow, guys, that didn't go well. So guys, the bottom line is this. This stuff is really difficult to teach. It's actually difficult enough to teach, and this is a big mistake I made when I started teaching. You understand that well, maybe you don't know this. There's all sorts of chat groups out there for chemistry teachers. Imagine how much fun that would be, right? You should sign up for these. So there are all these chat rooms that you can sign up for where there are just chemistry teachers talking about how to teach chemistry things. But the problem is that a lot of them are proctored by university professors, and I was a part of this chat group. Chemistry teachers are moving forward. We all sort of hit quantum theory about the same time. All of a sudden, this chat room lights up with all of this stuff about energy level, sublevel, orbital spin. And then all of a sudden, these university professors start chiming in. And basically, the tone of what they were saying was, your students are too dumb to understand this. You are too dumb to teach this. Leave it alone and let us do it when they get to college. Pissed me off. So I decided I was going to get good at this. And so guys, this is some of my best work. This is how I devised to teach you energy level, sublevel, orbital spin. If you had me last year, this is just going to be a retelling of the way we did this last year. If you had Miller in the past, I frankly don't know how he taught this, and that's not a slight on Miller. I really don't know how he taught it, but this may be new to you. But guys, what we're going to do is we are going to do this as review. This is going to happen appropriately quickly. So guys, your responsibility is to ask questions. So as we go through this, if there are things that you would like further explanation on, I would love to do that. But guys, the bottom line is this. You ready? Here's what we're going to do today. Uh-oh, the in baskets are in the way. But guys, we've got this idea of the Bohr model. These electrons moving around the nucleus in discrete orbits. We call that the planetary model. As they started to develop this model further, as they started to collect and analyze the light that these electrons were emitting as they fell, they found surprisingly that the electrons that were in an energy level, say for example energy level 4, when they fell to energy level 2, they were not all releasing the same amounts of energy. We found out later the explanation for that was because they weren't all the same. 2 of the electrons release the same energy, 6 of the same electrons release the same energy, and 10 of the same electrons release the same energy, which later we found out were the S, P, and D sublevels. So what we're going to do today is we're going to take the Bohr model and we're going to bring into the conversation the idea that these aren't just energy levels, but energy levels are composed of sublevels. Sublevels are composed of orbitals. And how are the electrons in an orbital different from each other? They have opposite spins, which literally means electrons are polar. You can think of them as having a north and south pole, and one of them will be oriented up. Well, there is really no such thing as up on a subatomic level, right? But one of them, they're oriented opposite of each other. For those of you that have taken physics, the term that we actually use is angular momentum, and their angular momenta are out of phase with each other. So here's the way this goes down. Guys, this is where Bohr got. Bohr described electrons as being in energy levels, which later we described with what is called the principal quantum number, which is the size of the energy level. And then when we stop thinking about these electrons as being in orbits and think of them as being in clouds, this then becomes the size of the cloud. The values on the periodic table, as you may remember from that surprising day when you figured out that the entire periodic table is based around the structure of energy level, sublevel, and orbital. The values on the periodic table range 1 through 7. We know the capacity of energy levels because it's given by the 2n squared rule. And then as n increases, some things change. This is now going to make more sense to you. But because you are all writing rather than learning, I will stop so that you can catch up, so that you can learn rather than write. Guys, everything we're doing today is review. I would suggest your most appropriate response would be to not take notes and grab your notebook from last year, because they're all in there. Literally, guys, I just hijacked 2 or 3 days of notes from last year and pulled out the important slides and turned them into this. So the 2n squared rule tells, and guys, again, please ask questions because I know that review means we are reviewing. So if you're not sure, let's talk. So the 2n squared rule tells us how many electrons can be in an energy level. So this is energy level 1, 2, 3, 4, 5, on out to 7, right? So how many electrons can be in the first energy level? Well, plug in 1 for n. So 1 squared is 2. No, 1 squared is 1. 1 squared is 1 times 2 is 2. 2 squared is 4 times 2 is 8. 3 squared is 9 times 2 is 18. It's the number of electrons that can be in each of the energy levels. Is that coming back to you?
Yeah, because, okay.
Yeah, so then remember the idea is that here's the 2 electrons in the first, here are the 8 electrons in the second, here and here and here are the 18 electrons in the third, and so on. Is that okay? Okay, so guys, let's talk about this. As the value of n goes up, there are 3 things that increase about these energy levels. The first one is the size. That one you just know intuitively. As the value of n goes up, the circles get bigger, the clouds get bigger. Guys, the second thing that we know that increases is the energy. To a maximum of what? 0, right? That's everything we talked about last time. As n increases, the energy of the energy levels go up by becoming less negative to a maximum of 0. And then finally, the capacity of the energy levels increases. And as Everett pointed out, that capacity is predicted by the 2n squared rule. Yeah, Taylor. Yeah? Yeah, so the idea is this, that the energy of these energy levels is an association with the nucleus. So when we get all the way out here where the electron is far enough away that it's no longer attracted to the nucleus, we say that its energy is 0, because what that really means is 0 attraction. Yeah, but then the thought is that this is the electron that is most attracted to the nucleus. But because we give those things negative values, as we go up, the numbers become bigger by becoming less negative. We okay? All right, so guys, this is the Bohr model, but remember it doesn't stop there. Again, as they were studying these electrons in these energy levels, they found out that they weren't all the same. Schrödinger came along with his wave equations and said, no, it's not just energy levels. The energy levels are broken down into sublevels. The sublevel quantum number is L. By the way, guys, you don't need to know those for the AP curriculum anymore. No longer do you need to know N, L, M, and S. Those are gone. They're still good to know, but there used to be these horrible questions on the AP test that would say, if N equals 3, and if L equals -2, and if M is equal to +2, what are the possible values for S? It was lovely. Okay, so guys, energy level, sublevel. So how many sublevels can be in an energy level? And the answer, almost poetically, is N. The number of energy levels, sublevels in an energy level is N. And you may remember what that means. The first energy level has 1 sublevel. The second energy level has 2. The third has 3, and so on. And those energy levels are given names, S, P, D, and F. Those were, in fact, originally names. They stood for simple, primary, diffuse, and fundamental. You don't need to know that either. But they were actually abbreviations for descriptors. But guys, what you need to know is what they look like. What does the S sublevel look like? Spherical. What do the P sublevel orbitals look like? Dumbbells. The D's are the clover leaves, and then the Michelin man with the thing around his belly. And then, guys, the F's are those 4-leaf clovers that are all messed up. Remember those? Okay. So we've got energy levels broken into sublevels. Sublevels are then broken into orbitals. Orbitals are the spaces that the electrons actually appear to occupy. Remember, guys, that they actually don't occupy those spaces necessarily. They are positions of highest probability. And then, guys, finally the spin. Oh, that should actually be up here. There we go. And then, guys, finally the spin quantum number is S. The spin, again, is a description of the orientation of the poles of the electrons. And in order for electrons to pair in an orbital, they have to have opposite spins. It's that polar opposition that overcomes the repulsion of the negative charges and allows them to pair up. And then, guys, the values for these numbers are plus and minus 1/2. Again, with the idea that up and down really is senseless on a subatomic level, but we just arbitrarily say 1 is spin up, we call that plus 1/2, 1 is spin down, that's minus 1/2. So guys, there you go. Drinking from a fire hose, that is all of the nuts and bolts of quantum theory. What we're going to do now is play with it. You're going to stop taking notes because there's no way you'll keep up, and you'll find that this will all come together. But let's do questions. Yeah. So yeah, it's a good question. So fundamentally, we need to understand that what they are describing is the polar opposition of the electrons. That's what you need to know. But the bigger answer is, what are these variables N, L, M, and S? And the answer is, these variables are the variables in Schrödinger's wave equations. So, for example, if you plug in N is 1, S is 0, wait, got to think about this. N is 1, L is 0, M is 0, and then S is 1/2, and you graph that, you get a little circle. Then if you plug in 2 and 0 and 0 and plus 1/2, you get a bigger circle. And then if you plug in 2 and 1 and 0 and plus 1/2, you get a dumbbell shape. So these are the variables in the wave equations that predict these shapes.
So wait, so is M just the amount of electrons?
No, M is the specific orbital. So the values, let's do the second energy level. So the second energy level, N is 2. The sublevel number for the P is 1. So then, no, not 1p orbital. So sublevel is, so S is 0, P is 1, D is 2, and F is 3. Again, this is stuff you don't need to know. But, so let's talk about, let's write this down so we see what we're doing. Let's talk about the 2p orbitals. So N is equal to 2. P, its L value is 1. Then the values for M would go -1, 0, and 1. And what do those values mean? Well, -1 would be the orbital that's up and down. 0 would be the orbital that's left and right, and then -1 would be the orbital that's in and out of the axis. So these numbers for M actually give you orientation three-dimensionally. Okay. So, and again, that how they line up, and that's the stuff you don't need to know. Okay, yeah. So you wrote that oh gosh, sorry, -1, 0, and +1. Yeah. Yeah. But again, they wrote that out of the curriculum. You don't need to know it.
Just one more. I feel like I'm inadequate if I don't understand this in any special way. What is the L1? I still get why it's called L1. Is that like?
So the idea is that L is shape. Okay, and our shapes are S, which is a sphere, P, which is a dumbbell shape, D, which are the clover leaves, and F, which are the really funky ones. The numerical values for these are 0, 1, 2, and 3. You guys good? Go ahead. Mm-hmm. They're magnetic. And there's a north and a south. Okay, so be careful with plus and minus, because you understand that electrons are negative, right? So it's not a plus and a minus. But remember the bigger picture here, and this is where this gets crazy subatomically, is that we are talking about electromagnetic waves, right? Electrons behave as waves, they also behave as particles. But the idea is that electrons have an electrical component, negative. Electrons also have a magnetic characteristic, literally a north and south pole. That is a radical combination. Camo. We can't even see the shirt, it's camo. So, but that's sort of this tension that we have between electromagnetic, because electrons have an electrical characteristic and a magnetic characteristic. They literally have a north and south pole, and so the idea is that those poles are out of phase when they pair up. Is that okay? You don't what? And it's interesting. You probably don't remember, but do this. So last year, the very first day of the unit when we taught you this stuff, you may remember we did an internet activity where we had you throw electrons and see if you could get them into orbit and stuff like that. That very first page of that experience talks about the electrical and magnetic components of particles in light. You may want to go back and review that. I was reviewing it yesterday, trying to make sure all the links worked, and it was frankly fascinating for me to reread that stuff. You may want to, the links are there on the General Chem site. So, guys, are we good? All right, so here we go. So, follow the thoughts. We're going to pull this together. Guys, for some, I'll just personalize this. For me, what we are about to do is bordering on spiritual. Because all of a sudden, well, I got to be careful, but it's so cool the way this all fits together. It's just amazing to me. So, energy levels to sublevels to orbitals with electrons that spin. Yes? Okay. How many energy levels are there? 1 through what? 7. How many sublevels are there? 4. What are they? S, P, D, and F. How many does the first energy level have? 1, it's an S. The second, 2, what are they? S and P. The third has 3, what are they? S, P, D. The fourth have 4, what are they? S, P, D, F. Then, guys, those sublevels are broken into orbitals. How many orbitals does an S sublevel have? 1 and it's a sphere. P sublevel, how many orbitals? 3. What are their shapes? Dumbbells. The D sublevel has how many orbitals? 5. Remember? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons, 2 electrons in an orbital. That means there's 5. Remember drawing the boxes? For all the D, you did 5. And then, Joey, how many are in the F? 7. Good? Okay, let's bring it all together. This is cool. Here we go. There's the nucleus of the atom. These lines represent these lines that we drew on the board as if these continue around into shells. Notice, guys, this is not drawn to scale, because if it was, this space would have to be significantly bigger than this space, because the space between the nucleus and the first energy level is significantly greater than the space between the first and the second energy level. So really the nucleus should be on the floor. Okay? Now, notice what's happening to the spaces between the energy levels. It's becoming ever closer. Can anybody talk to me about why, given what you now know? What is the denominator of the equation that allows us to calculate the energies? N squared. You get it? The energies are getting closer because the denominator of the equation that describes these energy levels is a squared relationship. So we're talking about dividing by numbers like 4 and 9 and 16, and they're getting ever bigger, so the spaces are getting ever smaller. So now, guys, let's start pulling this together. N is energy level, L is sublevel, M is orbital. So here's what we know. These go not 1 through 4, but 1 through 7. And guys, again, what these rungs represent are these clouds which we've been talking about all along. Now, let's talk about how many electrons are in these energy levels. How many electrons are in the first energy level? 2. That's the 2n squared rule. How many in the second? 8. How many in the third? 9 or 18. And then how many in the fourth? 16, 32. And then it goes up to 50 and on from there. You good? Okay. Now, guys, let's talk about sublevels. So first energy level, how many sublevels? 1. And it is an S sublevel. So remember, guys, first energy level has 1 sublevel of it's an S. Now, some logic. If there's 2 electrons in this energy level, and if that energy level only contains 1 sublevel, how many electrons have got to be in that sublevel? Both of them, right? It's kind of like this. If you have a neighborhood that contains 2 houses, it's a new neighborhood, a new development. So if you have a neighborhood that's got 2 houses built in it, but there's only 1 street in the neighborhood, how many houses have got to be on that street? Both of them. There's nowhere else for them to be. Similarly here, if we have an energy level that is only broken into 1 sublevel, which is a crazy idea, both of these electrons have got to be here. Now let's go to orbitals. Guys, how many electrons can go in an orbital? How many electrons go in an orbital? 2. What is true of those 2 electrons? Opposite spin. So, if we need space for 2 electrons, how many orbitals does it take to house 2 electrons? 1. And it looks like this. This is the relative size and shape of the 1s orbital. You understand that it's a sphere, and in fact, there's only 1 of them because we only need 1 orbital to house the 2 electrons in the 1s sublevel. Now let's go to the second energy level. Remember, so we go to the second energy level. How many sublevels in the second energy level? 2, and they are S and P. Now, guys, this is the thing that led Bohr and then Schrödinger to start thinking more deeply. When the 8 electrons from the second energy level fell to the first, they didn't all have the same amounts of energy. So what we found out is that we've got the 2s and the 2p. The 2 electrons in the 2s did have the same energy. But then we found that there were 6 other electrons in the second energy level that had more energy than the 2 in the s. We'll talk more about this when we do PES. But the bottom line is this. The second energy level contains an S sublevel and a P sublevel. We've already established that 2 electrons go in the S, so the remaining 6 have got to be in the P. You okay with that? Okay, now we're now on orbitals. How many orbitals does it take to house 2 electrons? 1, and it's this, the 2s. Now guys, how is the 2s similar to the 1s? They're both spheres, but how is the 2s different from the 1s? It's bigger. Okay, now we're ready to talk about the 2p. If we need space for 6 electrons, how many orbitals do we need? 3, and their shapes are dumbbells. So do this with me. How are the 2p orbitals similar to the 2s? How are the 2p's similar to the 2s? Size. They are approximately the same size. The 2p are a little bigger than the 2s, but they have approximately the same radius. So how are the 2p obviously different than the 2s? Shape. Now let's do this. So guys, let's stop here and let's have that moment that you got to enjoy last year. We've got 2, 4, 6, 8, 10. 10 electrons around the nucleus. That would make this atom neon. So what does neon look like? It looks like this. Do you remember? What is, and I'll try to highlight it, what is this space? Oh, come on. What is that space right there? The 1s. What is this space right here? The 2s. It is similar in shape to the 1s. It's just bigger than this, and this, and this represents what? The 2p. You will notice that it is a little bit bigger than the 2s, but not bigger enough to be in the 3rd energy level. And you'll notice that there are, in fact, 3 p orbitals oriented 90 degrees to each other. And as predicted, that's room for 6 electrons. And this is what a neon atom looks like. Do you remember that magic moment? For some of you, you may be having the magic moment now because it was going so fast last year that maybe you needed a second shot at this. But guys, that's the idea behind these energy levels and sublevels and orbitals. Questions pertinent to what we're doing? Go ahead.
So, the orbitals can overlap.
Definitely do they overlap. All over the place. Yeah.
So, I know that there's obviously conflict going on there because it's the same charge, but is the conflict just not big enough to make everything sort of explode and all the electrons go flying in?
Exactly. And so, guys, let's talk about this. Why do these electrons occupy the spaces that they do? And we're going to talk about this from a couple different angles. So why do they occupy a small sphere, a big sphere, and then 3 dumbbell shapes? And guys, the answer is because it is the best resolution of stress. Because guys, if you're an electron hanging out in this atom, there are 2 forces that are acting upon you. What is the attractive force that's acting on you? The attraction to the nucleus. What are the repulsive forces that are acting on you? The repulsion of the electrons. So the most efficient way to resolve the attraction with the repulsion is if the first 2 electrons go in a small sphere, the next 2 electrons go in a big sphere, the next 6 electrons go in big dumbbell shapes. That's why they occupy these spaces, because they're trying to get as close to the nucleus as they can, but as far away from each other as they can. Is that okay? Okay, but then we end up with sort of a weird tension. And guys, the tension is this. Are these electrons actually moving throughout these spaces? They are not. And guys, this is where we need to sort, and we don't need to do this a lot, and I don't want to run down this rabbit trail, but guys, you've got to understand, and you can spend more time on this in college if you choose to. Guys, there is something fundamentally crazy about electrons. This electron right here can actually move from here to here without traveling through the space in between. Or that electron can travel from here to here by traveling through all possible paths from one spot to the other. Guys, you've got to understand that when we draw these simplified models of atoms, even though it looks relatively complicated, understand that we're only beginning to touch on some very amazing realities when we talk about quantum subatomic physics. So these models work, and they're not wrong, but you've also got to understand that electrons are not like bees buzzing around a light. They actually move in ways that are so counterintuitive to our own experience that, first of all, it sounds like people are lying to you. But then once you wrap your head around the idea that they're not lying, and in fact electrons can move from one place to the other without traveling through the space in between, you start to realize that the only way to really describe that is mathematically, and thankfully we don't have to do that. So guys, we're going to let that be enough. I'd love to answer a question about energy level, sublevel, orbital spin, but we are not going to run down the rabbit trail of the unique behaviors of subatomic particles. So
you said that this is the best way, like the best positioning in order to relieve stress or something.
Correct.
So does that mean that it's not particularly good, but it's the best that they've got, and they just have to stick with it?
Well, so everything in the natural world is a resolution of tension, right? That's why bonds form, because energy is released. So if you want the big answer to why does anything happen, tying back to Gibbs free energy and spontaneity, why does anything happen? Because it releases energy. So why does this happen? Because it releases energy. This is the lowest possible energy state that these atoms can get into, and so that's what they do. You guys okay with this? So gang, let's keep going. Third energy level, you ready? The third energy level, there's my pointer. The third energy level, oh, I'm drawing white dots that you can't even see. The third energy level, guys, is broken into how many sublevels? 3, what are they? S, P, and D. They go like this. We know that there are 2 in the S and 6 in the P because we already established that. So how many are in the D? Got to be, right? 18 minus 8 is 10. So we've got the S and the P. How many then orbitals have got to be in the D sublevel to house 10 electrons? 5, and they look like this. But again, we draw them as boxes with arrows. Then, guys, the fourth energy. What's that?
Could you go back to that picture?
Yeah. The pictures of the Ds? Yeah. I think so. Like that? Oh, I didn't know you guys wanted to talk about this. Go ahead, Elisa. Okay, so here's the problem. You've got, and I'm not accusing you of anything, but you've got to break, if you're there, you've got to break away from this idea that those electrons are actually moving in that space. That is simply the place of highest probability. And so it turns out that when you start packing multiple electrons around a common nucleus, the resolution of stress would predict that that electron would have its lowest energy position when it occupies that space. Yeah, crazy. Go ahead, just a second, go ahead.
So these are kind of like placed within all the others as well.
Well, that's this, right? Yeah, so 1s, 2s, 2p, well, that's, I don't know how they drew this, but yeah, it's an all of this is happening around everything that's happening beneath it. Yep, absolutely. Yeah, go ahead, Hunter.
Do we have to know the names of the d orbitals? Like,
The dx2, y2, no. Did you do that in the, oh, you did? No, you don't. Go ahead.
so the one that's right over the shape one.
This guy?
Yeah. Isn't that the same as the d orbital?
It's not, because this one's oriented, I don't know which is which, I can't tell, but this one is oriented on the x and y, and this one is oriented between that plane.
Yeah, but for the key ones, they're on the axis. So
Oh, I see what you're saying. Yeah, absolutely. But understand that this is bigger than, or well, no, it's not even real. It's a little bigger than this. But again, as Jared was getting us to think about, the overlap just becomes more and more complex. But if we get comfortable with the idea of these being probabilities, then we get comfortable with the idea that they're also getting out of each other's way. You guys okay? Go ahead. No. So all of this was initially predicted mathematically. And realize not just mathematically, but just mathematically with hydrogen, right? And so when Schrodinger was solving these equations, he was solving these for single electron systems. And so if you take an electron, if you take the one electron from hydrogen and if you energize it, it can occupy a bigger sphere. It can occupy any one of these bigger dumbbells. It can occupy any one of these spaces. So you start to think about, and this, guys, this idea causes some real tension because we're talking about the idea that these spaces exist because they're resolutions of forces, right? But when you promote electrons to these energy levels, they occupy these spaces even when there aren't electrons pushing on them, as if these things were planned, as if they were present, even if the other electrons that should be there to cause them to be present, even if they're not there, electrons still behave this way. So yeah, it's fascinating. There's another fundamental reality in the subatomic world that causes them to occupy these spaces beyond the resolution of forces. And to understand that, we have to talk about waves, because these are actually, they all tie back to Schrodinger's work with waves. Because when we start thinking of these electrons as not as particles but as waves, these are actually waveforms that are self-reinforcing and therefore stable. That's an angle we don't have to take. But that's actually how Schrodinger first came to these. So yeah, it's crazy. Yeah, go ahead, just a second, go ahead.
So they're not, atoms aren't symmetrical because like everything so far has been symmetrical except the last one because it's just around the XY plane and not in the Z direction.
Yeah, so it's an interesting question, Carson, and we're going to talk about that question of symmetry. Oh gosh, I think in the next unit, it may be the unit after. And we're going to talk about the difference between average symmetry and instantaneous symmetry. Because what you've got to understand is that these electrons are moving crazy, right? And so the average of these, well, it's not great, but if you look, this blob is made up of all of this, right? And I mean, heaven knows this was drawn by hand, but there's still a symmetry to it, right? There's so much going on there that if you look at this, we might say that it's somewhat symmetrical. But if we then understand that each one of these clouds is actually a space occupied by an electron, and we don't even understand how those electrons are moving around the nucleus, but we know that they are, they're not stationary for sure. If we could then turn this into a video and hit pause at any given moment, no, the atom is not symmetrical. Therefore polar, therefore atomic substances can exist as liquids and solids. We're going to talk more about that later. But on a macro scale, we do think of them as being symmetrical, and therefore they should be nonpolar, but we know in reality they are polar because we have atomic liquids and solids. Yes. Yes. Right, but understand that that is symmetrical. The donut is symmetrical about the nucleus. Correct, but if you go the Z-plane, it still creates symmetry. If I had an inner tube around me, assuming that your body is in fact symmetrical, if I had an inner tube around me, it wouldn't destroy the symmetry of me, because no matter how you cut me, there would still be half an inner tube in some fashion. You know what I'm saying? Well, it does. I think our return on this investment is going to be low. I'd love to talk with you, but let's just be comfortable with the idea that on average they're symmetrical. Eliza, you had a question.
So, do electrons, if you treat them as a particle,
They do, yeah.
So what happens to this?
Sure. And so now we get back to what's called the Heisenberg uncertainty principle. So, and this is that tricky bit, right? That says that there's something unknowable about electrons. And so there are two things that are knowable maybe about electrons: where they are and where they're going. And so when you treat electrons as particles, if you find out where it is, it's now impossible to know where it's going. If you found out where it's going, it's now impossible to know where it is. So you can't know both of those things simultaneously, which means that this model fundamentally falls apart when you treat electrons as particles, because developing this from a particle view is fundamentally impossible. There's something fundamental, I keep saying fundamentally, but it really is, there's something fundamentally unknowable about electrons. And it's not because we aren't doing experiments well enough, it's because electrons, again, fundamentally won't allow us to ask it that question. Yeah, isn't that cool? Yeah, go ahead.
Is atomic polarity why all noble gases are effect gases? Because the shells are filled with electrons
Yes. Yes, that's why the noble gases are gases. Yes, go ahead.
So do these electron clouds almost like so I know the circles like space station.
Yes.
But these like the dumbbell shapes kind of like move, or do they just stay there and that's what electrons do?
Yeah, Jared, it's an interesting question. So if we understand that these are spaces of probability, their orientations to one another have got to be relatively fixed. So if you think about them as being averages over time, then their locations relative to one another would be fairly consistent. Well, in as much as if you spin the entire atom, they would be moving, but really the only thing you can talk about as a point of reference is relative to each other. They would stay put, yeah.
In response to Keel's question, carbon then be a gas because it's electron structure symmetrical?
And the answer is no, because experientially we know that it's a solid, but there are a lot of things that we need to talk about before we can tie those things together. Okay, so guys, let's continue on then. Okay, so now we're up to the fourth energy level. The fourth energy level contains how many sublevels? 4, S, P, D, and F. And then we had this scary moment where we realized that the 4S actually tucks itself underneath the 3D. So it goes S, P, D, and then F, 14 electrons in the F, as represented by these sublevels down here, which you found out was in fact the F sublevel. There are 7 F orbitals, and you can look up their shapes. I don't think I brought it. Oh, no, I didn't. So you can look up their shapes as well. But then, guys, it just continues on up from there. Last year, I actually offered as an extra credit challenge to do this all the way through the 7th energy level. I frankly don't recall if any of you took me up on it. But whether you did or not, this is all the structure of the periodic table. We've got the energy levels as the horizontal rows. We've got the periods as the groups S, P, D, and F. And guys, this is the structure of the periodic table. Now, the point that we didn't make last year is this. Guys, give me a time frame. When did Schrodinger start thinking about his wave equations, roughly? What period of time? 1920s, the interwar period of time. Guys, when did Mendeleev come up with the periodic table? Yeah, well, actually, I think it was even earlier than that. It was somewhere on the order of 100 years before SPD and F. So, guys, we had this fundamental structure for the periodic table long before we knew this. So how did Mendeleev put the periodic table together? He did it based upon mass and reactivity. But doesn't that make sense? When Mendeleev put the periodic table together, he put all of the elements that react the same in a group. Then as he was putting them in order by mass, he found this periodic repeating and he formed this periodic table. Then when we found out about S, P, D, and F, all of a sudden what we know about electron structure, catch this, what we know about electron structure mapped perfectly onto a table that was based upon reactivity. Why shouldn't that be surprising?
Determine everything.
Yeah, electron structure determines reactivity. Why do all the alkali metals, remember group 1, why do all the alkali metals react the same? Because they all have one valence electron in their highest S sublevel. So guys, it shouldn't be surprising that a periodic table formed on reactivity and a periodic table formed on electron structure should be the same because electron structure determines reactivity. Okay. So guys, it was at this point then that we had 2 or 3 more days in class where we started talking about some fundamental ideas about atoms and then their structures. So with all of this, guys, these are the things that you should be able to do, and we can talk about them as we go if we need. So this you may want to include in your notes. So first of all, the Pauli exclusion principle. We talked about this last year. This is one of the things you need to know for the AP content. So let's just, here, I can turn the lights on. Let's just talk about it now. So guys, the Pauli exclusion principle, most of you probably know it and just forgot the name. The Pauli exclusion principle just says this: no 2 electrons in an atom can have the same 4 quantum numbers. No 2 electrons in an atom can have the same 4 quantum numbers. Do I need to do it again? No 2 electrons in an atom can have the same 4 quantum numbers. Did you all get it? So guys, what does that mean? Let me give you a real world analogy. If I wanted to know all of your guys' home addresses, there's one thing that I know for sure. Your home address is not 362 West, 700 North in Linden, Utah. You want to know how I know that? Because you don't live at my house. Guys, it's the same thing with electrons. If you have 2 electrons with the same address, they're the same electron. And that can't be. So you can think of these quantum numbers, energy level, sublevel, orbital, and spin, as being like an address. And no 2 electrons in an atom can have the same address, the same quantum numbers. Okay, now there's a thing called Hund's rule. Hund's rule basically says this: you don't fill the 2s until the 1s is full. Remember how we place electrons? Where we go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and so on. That's Hund's rule. It's just a rule that says they always fill in that order. And then guys, finally this. You've got to be able to do orbital filling diagrams, and you've got to be able to do noble gas abbreviations. Now guys, the tricky part with this is your periodic table. That's all you got. So what does that mean? Well, do you want to fiddle with a couple of these? Would that be helpful? Okay. So you know what? I'm going to just sort of cherry pick the ones that I want to talk with you about. But why don't we do these together so we can talk about some important things? So let's do copper. Let's do copper together. So guys, and we're just going to allow copper to be our big old example of everything, and then we'll see how we do. Yeah. You want to see what I'm... Because you know why I picked copper. So guys, copper is right here in which sublevel? 3D, right? So we've got to build up to it. So in building up to it, we go 1s, 2s, 2p, 3s, 3p, 4s, 3d. Then guys, we need boxes. The boxes represent the orbitals. We know that the 1s orbital is a sphere. We draw it as a cube, as a square. 2s is also a sphere. Draw it as a square. The 2p are actually the 3 dumbbells. We draw them as 3 squares. The 3s is an even bigger square. We draw our bigger sphere. We draw it as a square. The p's are the dumbbells. We draw squares. The s's is a sphere. We draw a square. And then the 1, 2, 3, 5 in the D. You probably guessed this when I taught this to you last year, but this gets nutty. Teaching this to general chemistry, imagine how many stinking arrows I draw in a year. Teaching this to 5 different sections of chemistry, you just have nightmares about arrows. Okay, so guys, when we are doing copper, we know that copper has got 29 electrons. So let's remember, electron 1 goes there. Where does electron 2 go? Paired up. Says who? Hund's rule. Electron 3 goes here. Electron 4 does not also go there. Says who? Pauli exclusion principle. Do you get it now? So this would be 4, 5. Now, guys, where does 6 go? Unpaired. Says who? Hund's rule. And then 7, and then 8, and 9, and 10. And guys, I know you probably remember this, but what do you do if you lose count? Well, the last electron in the 2p is electron 10, and you just go on from there. So we go 11, and 12, and 13, and 14, and 15, and 16, and 17, and 18, and 19, and 20, 21, 22, 23, 24, 25, 26, 27, 28, and 29. And that's copper. Let me play for a minute. So guys, are you okay with copper? You're okay? Okay, now, another thing that you've got to be able to do with this is what is called the noble gas abbreviation. So let's do this a couple different ways. So to do the noble gas abbreviation for copper, we go back to the previous noble gas, which is argon. And then, guys, you should be able to do this without even looking, obviously without doing this, because past argon, we've got these 2 electrons, which are where? 4s. So if you remember, we go 4s2. And then we've got these 9 electrons, which are in the 3d. And you should be able to obviously do those without drawing the orbital diagrams first. Okay, now guys, let's play a little game. No. I'm going to get this out of the way. So guys, talk to me about a copper 1+ ion. Are we adding or removing an electron? Which one? Not that one. It's always out of the highest S or P. So guys, in order to form that ion, we do that. So now guys, talk to me about this. What about a copper 2+ ion? What do? Take them both, take them both out of the S. So now guys, what about a copper 3+ ion? You can't. Copper cannot be +3. It doesn't have another valence electron to remove. So now guys, let's put these electrons back, and we need to have a conversation that we didn't have before. So guys, if you look at copper, and I know you don't have this on your periodic table, but from experience you may know that copper does go +1 and it does go +2. Now, you've got to be able to explain why, and I think this is maybe where your head was going, maybe? I don't know, maybe. Okay, so guys, let's talk about why. if copper goes +2, what's happening? Both of the electrons come out of the 4s. That's easy to explain. But guys, what if copper goes +1? What's happening? And it's not as simple as the idea that this electron is just coming out of the s. Because the reason is this. This is not what copper looks like. If you dig up a copper atom out of a penny or wherever you get it, this is not the electron structure of copper. Let me show you. Guys, this is actually the electron structure of copper. Copper in its elemental form actually does not have 2 electrons in the 4s. What happens is one of the electrons in the 4s sublevel of copper actually falls into the d sublevel. Why would it do that?
You want me to answer?
Yeah.
Okay. It's because 3D works better when it's full.
Yeah.
It's more stable.
Exactly. And so fundamentally, what is it doing? Releasing energy. Guys, it turns out that this atom is more stable when the D is full and the S only has 1 valence electron. In that configuration, we have a full sublevel and a half full sublevel, and that configuration is more stable than this structure where we have a full sublevel and a randomly filled sublevel. So now you're going, crap. So guys, let's sort of unpack this. First of all, if you look up the electron structure of copper on your periodic table, you'll... What does that say? It should. Mine doesn't. What is it? That says... That's interesting. That's a typo. So guys, it should, and it does. On these, it does in fact say copper is 4s1, 3d10. Because that's in fact what does happen. But now guys, you are all, I think, understanding that you're in trouble. Because guys, if you allow your, well, never mind, you don't have this in front of you, so let me just tell you. There's a lot of atoms in the d sublevel that do this. You see a lot of mobility for the transition metals where electrons are moving in and out of S and D sublevels to create these conditions of maximum stability by unfilling and filling sublevels. How on earth are you supposed to know? You're not. So guys, the bottom line is this. On the AP test, here's what you've got to understand. You have got to understand the orbital filling diagrams based upon the trends. So if they ask you for the orbital filling diagram for copper, they would accept 4s2, 3d9. See what I'm saying? But if there were a question on the test that says which one of these electron structures explains why copper goes +1, then you need to understand that it's because one of the electrons out of the S into the D, and that one electron is then available to go away as an ion. So you've got to understand the implications of these electrons moving around, but you don't have to know the electron structure on the periodic table. This electron comes back and leaves. Yeah, when the first electron promotes, when the first electron leaves, this one comes back and then it goes away. Yeah, that's a good question. So guys, do you understand how they're going to play that game with you on the AP test? You're okay? Go ahead. Oh yeah, it goes 7, 5, 3, 4, 2. Yeah, it's all over the place. You can explain every possible charge that manganese takes on by looking at how you could push where is manganese? It's By pushing electrons between the 4s and the 3d, you can create distributions of electrons between the 4s and the 3d that explain every charge that it takes on. Yeah, go ahead, Josh.
So on the test, if you were to answer the correct form, like if they're asking what's the configuration?
Yeah, and if you just, hey, I know that it's 4d1, 3s10, or 3p10, or 3d10, you bet. They would accept both. Yeah, to be honest with you, you won't see those questions on the test anymore because they claim to have written them out. But you may see something related. Yeah.
Would it be fine for chromium too? Is chromium acts the same way?
Absolutely. Yeah, and manganese and all other, and as you know, it's the transition metals that play these games. Oh yeah. Yep. It's nuts. So guys, that's it. So the homework today is intended to allow you the opportunity to sort of stick the dipstick in the engine and make sure you're all full up on oil. You got to this is really your opportunity to make sure that you're where you need to be. So when we get back on Monday, we'll visit this homework, and then we will talk about PES. PES is not in the book. And the homework will not be out of the book. So I'll be handing you lots of handouts. But guys, you're going to love PES. It's really, frankly, fascinating to teach. It's lovely stuff. And it all reinforces these ideas. So, bump, 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 bump. There you go. There's your homework. We've got about 7 or 8 minutes left. While you're checking out your homework, guys, these are your grades tomorrow. Zach, you're going to stay. Everett, you're going to stay. Josh, you're going to stay. Bus. Shelby, you know what you're doing. Nathan, you're going to stay. Spencer, you are going to stay. Carson, you are going to stay. Spencer Miller, you are going to stay. McKay, you are going to stay. Parker, you are going to stay. Alex, you are going to stay. And everybody else will be free to go. And Shelby, you understood what I was saying to you, and you're going to stay, right? Just because you want to? Yeah. Yeah, just let me stop recording. Oh, wait, you're saying you have an NC in Reggie's class.